20,000 sorted numbers. Find two numbers that add up to the target. This problem is called two-sum. The obvious way is two loops. Take one number, then try it with every number after it. It works, but it checked 149 million pairs and took 12.7 seconds. Now run the same question again. Same list, same target, same answer, 19,999 steps, 3.7 milliseconds. No cache, no pre-computation. It simply skipped almost everything. That is the two-pointer pattern. Two pointers means we keep two positions in the data and move them by a rule. It is often taught as a trick to memorize. It is not a trick. It is one idea. Before moving a pointer, we prove that everything it leaves behind cannot contain the answer. Once you understand that, you can derive the pattern yourself. By the end, you will know why it works, when you can use it, how it fails when the rule is missing, and the three common shapes it takes. All in Python, all measured. Start with what we are replacing. Two nested loops over the same list are not one line of work. They are an area. Every pair is a cell in a grid. Rovi, column J. The inner loop checks one cell at a time. 20,000 numbers create 199,990,000 cells. So the real question is not how to make each check faster. The question is how to avoid checking most cells at all. Here is the idea. Sorted means the numbers go from smallest on the left to largest on the right. Put one pointer on the smallest number and one on the largest. Add them. If the sum is too big, ask what that proves. The right number is too large with the smallest number still available. Every other partner for that right number is even bigger. So every remaining pair using this right number is also too big. None of them can work. That whole column is gone. If the sum is too small, use the same logic from the other side. The left number was paired with the biggest possible partner and it still fell short. Every other partner will be smaller. So that whole row is gone. That is the pattern, not two pointers moving around. One comparison removes a whole region. The code is short. Low starts at the front, high starts at the back. While they have not met, add the two numbers. If the sum matches, return the pair. If the sum is too small, move low forward. If the sum is too big, move high backward. No dictionary, no second list, no recursion, just two indexes. Also notice what the code does not check. It never checks whether the list is sorted. The code depends on that being true before it starts. Run it on 20,000 numbers. It finds the same pair as the nested loops index 10,000 and 10,001, 19,999 steps. Each pointer moves in one direction. Together, they cross the list once. That is why it is linear. There is no hidden trick. Just counting. Now break it. 6 values sorted. Target 15. It finds 4 and 11. Now shuffle the same 6 values. Same target. The answer is still there. This time it returns none. No exception. No warning. The output does not tell you the input broke the rule. At 20,000 values, the same thing happens. Sorted, it finds the pair. Shuffled, it says there is no pair, even though there is. So what did sorting give us? It gave us one sentence. Moving right cannot make the number smaller. That sentence is the license. It makes this claim true. This number is too big for everything left. Without sorting, that claim is false. After shuffling, moving right no longer means the number gets bigger. But the code still acts like it does. This is why sorting mattered. It did not magically make the answer faster. It created the order that made each pointer move safe. This is the main thing to remember. Before you move a pointer, name the property that makes the move safe. If you cannot name it, you do not have a two-pointer solution yet. So should you sort first just to use two pointers? Not always. Sorting gives two pointers the rule it needs. After sorting, moving low forward makes the number bigger. Moving high backward makes the number smaller. That is what makes the discard safe. But sorting has a cost. If the data is unsorted and you only need to answer one two-sum question, a dictionary is usually better. A dictionary answers it in one pass. Here, the dictionary takes 3.1 milliseconds. Sorting first and then using two pointers takes 7 milliseconds. You paid in login just to make two pointers possible. For one lookup, that is usually not worth it. And even when the list arrives already sorted, the dictionary is still slightly faster here, 1.6 milliseconds against 2.3. So speed is not the argument. Memory is. The dictionary held 574 kibibytes. Two pointers held 200 bytes. So the rule is this: use two pointers when the order is already there, when memory matters, or when you will reuse the sorted order. Do not sort just because you want to use the pattern. Now, a second problem. This one is called container with most water. You are given a list of wall heights. Each number is the height of one vertical wall. Pick any two walls. Together with the ground, they form a container. The water it can hold is the distance between the walls times the shorter wall. So if the walls are 7 positions apart and the shorter wall has height 7, the area is 49. The goal is to find the pair with the largest area. Nothing is sorted here. There is no target sum. But there is still a discard rule. Start with the wall at the far left and the wall at the far right. One of them is shorter. Every other pair using that shorter wall will be narrower, and the height still cannot be more than that shorter wall. So every one of those pairs holds less water. That shorter wall is done. Move the shorter wall inward. With 20,000 walls, the brute force version checks about 200 million pairs and takes 42 seconds. The two-pointer version takes 19,999 steps and 7.5 milliseconds. Same answer, different rule, same pattern. Remove a region, then never go back. Third shape. This one is often called a sliding window. Both pointers move in the same direction. Find the longest run of values whose sum is no more than k. Grow the window on the right. When the sum gets too big, move the left edge in until the window fits again. Why does the left edge never need to move back? Because every value is positive. So growing the window can only increase the sum. Shrinking it can only decrease the sum. If a window starting here is already too large, every longer window starting here is also too large. That starting point is finished. 8 values, 13 pointer moves. Each value enters the window once and leaves once. Now add one negative number. Same code, same limit. The window says the longest run has length 4. The real answer has length 5. Once negatives are allowed, growing the window can make the sum smaller. So the left edge may throw away a start point that is needed later. Same failure as the shuffled list. The required property disappeared and the code did not check. The last shape is fast and slow pointers. You may have seen this with linked lists. A singly linked list has no index. You cannot jump to the middle, and you cannot start from the far end because every node points forward and nothing points back. The only way to reach the end is to walk the whole list. So the second pointer cannot be placed. It has to be earned by moving twice as fast. When the fast pointer reaches the end, the slow pointer is at the middle. One pass. No length needed. Now connect the tail back into the middle. The same two pointers can detect the cycle. Inside the loop, the fast pointer gains one position on the slow pointer at each step. So the gap keeps shrinking. Eventually, the gap becomes 0. They meet. For 1,000,000 nodes, storing every visited node costs 1,000,000 entries. This costs 2 pointers. One correction worth making, because it is the lesson again. That constraint was about singly linked lists. Make the list doubly linked and give it a pointer to its tail and the constraint disappears. You can put a pointer on each end and walk inward exactly like the sorted array. Same middle, same number of steps. Both parts matter. Previous pointers alone are not enough. Without a tail, finding the end still costs a full pass, which is the pass that fast and slow exist to avoid. And none of it changes cycle detection. A list with a cycle has no tail to hold, so fast and slow stays the answer there. So the shape is not a property of the pattern. It is a property of what the structure lets you reach. Now step back. These three problems look different, but they share one thing. A pointer moves in one direction and never comes back. That is where linear time comes from. Each pointer takes at most 10 steps. Two pointers means at most 2n moves. The work stays linear. But the pointer is allowed to never come back only because some property makes that safe. Something about the data proves that what was left behind cannot contain the answer. Before using two pointers, ask what does moving this pointer prove I can ignore? No proof, no two pointers. That is the whole test. Here is everything in one file. 4 functions. The first line of every docstring is the precondition. ToSum needs the list to be sorted. Most water does not need sorting. Its own area rule gives the discard. The sliding window needs values that are never negative. The linked list version needs only a next pointer. The file does not check these rules. That is not carelessness. That is the real shape of the pattern. The correctness comes from the argument you make before writing the loop. Pause here and copy it. It runs on the Python version in the corner. 149 million pairs, or 19,999 steps. Same list, same answer. The difference was not the loop. The difference was knowing which part of the grid could not contain the answer